Welcome to another of the My E-Biology Teacher podcasts. I am Mr. Doc, and today we are going a little off the reservation, and we're going to be talking about chemistry. But wait, Mr. Doc, this isn't a chemistry class, this is a biology class. I know, but if we think about it, life is a whole bunch of chemical reactions that happen all the time. So, if we really want to understand life, we want to understand biology, we're going to have to start with chemistry because it has a whole lot to do with it. So in today's E-Biology Teacher podcast, we will be discussing matter and what it means. We're going to talk about elements, atoms, compounds, and molecules. We're going to talk about chemical bonds, specifically covalent and ionic bonds. We're going to classify the parts of chemical reactions and talk about the kinetic theory of matter and what it has to do with us. Now let me first say, before we get too deep into this is not a chemistry course. So the point of this conversation today is to teach you what you need to know about chemistry to understand biology. There's obviously a lot more to do with chemistry than we're going to get into. So keep that in mind. We're just going to hit the basics today. As a matter of fact, most of this you've had before, but we'll see what happens. You know, maybe this will be a good reminder, or maybe this will be the first time you've heard it. All right, so let's take a look at what matter is. First of all, everything in the universe is made up of matter. Matter is defined as anything that has volume and mass. In other words, it has mass and it takes up space. All matter is made up of tiny little particles called atoms, and atoms are the smallest unit of an element that retain all that element's properties. So an atom is unique, and if you have a whole bunch of atoms that are the same, they form an element. So we're all familiar with oxygen. Well, every oxygen atom is pretty much the same, okay? So if we have a whole bunch of oxygen, that's called an element, but every individual piece of oxygen is called an atom. All right, it's pretty simple enough. Now if we continue further, we can talk about atoms and what they are. Well, first of all, an atom is made up of 3 subatomic particles, the prefix sub meaning below. So these are smaller than the atomic level. Protons are positively charged particles that are located in the nucleus of the atom. And they are the things that basically tell an atom what element it's a part of. Now, hopefully everyone has seen one of these, the periodic table of elements. Now, you'll notice in the periodic table that there are these numbers here, and those are called the atomic number. The atomic number tells us the number of protons that are in each atom of that element. So every atom that, say, has 8 protons is an oxygen atom, and every one that has 9 atoms is a fluorine atom, and every one that has a 77 is an iridium atom. So there you go. Now we know how to figure out how many protons are in there. The number of protons really classifies the atom as what it really is. Now the number of neutrons on the other end are, and by the way, neutrons are these particles that are in the nucleus that have no charge, they really add heft or weight to the atom itself. So let's take a look at what that means. All right, so if we look at our periodic table, you'll notice there's a number. See fluorine right there? It's got an atomic number of 9, but it has a mass of 19. Well, a proton weighs 1 atomic mass unit, and a neutron weighs about 1 atomic mass unit. So if there are 19 atomic mass units per atom, we take the 9 minus 19, that leaves us with 10. There are 10 neutrons in the fluorine atoms, okay? Now that doesn't mean that doesn't change. We have a thing called isotopes, and we'll talk about isotopes later when we talk about carbon dating, when we talk about X-rays. But isotopes are when the weight of that particular atom might be different because that particular atom might have more or fewer neutrons, and that's when the nucleus starts to shake up and break up and do all kinds of fun radioactive things. All right, but basically speaking, to find out the number of neutrons, we take the number of protons, in this case 9 for fluorine, and we subtract it from the mass, 19. 19 minus 9 is 10. That gives us 10 neutrons. And remember that the electrons, which we're getting ready to talk about, weigh almost next to nothing. So that's not a whole lot of deal there. All right, so electrons are not in the nucleus. They are actually in the electron cloud on the outside. They have a negative charge, and they are responsible for bonding. And once again, electrons do not weigh that much. They really don't. However, we look here. Protons are positively charged. Electrons are negatively charged. Well, the negative charge of one electron is equal and opposite to the positive charge of one proton. Well, that means that for every proton we have to have one electron. That way we equal neutral. You see, proton is a positive charge. Electron is a negative charge. One positive plus one negative equals neutral. So if fluorine, which we've been talking about, has 9 protons, it means it has 9 electrons because they have to be neutral. If an atom is not neutral, meaning that it has a different number of electrons than it has protons, it's called an ion. I-O-N. Okay? An ion is an atom that actually has a charge because it's either lost or gained electrons. And going back to neutrons, by the way, a neutron or an atom that has multiple different numbers of neutrons, like it's got more or less neutrons than other atoms, it's called an isotope, which is also the name of the baseball team on The Simpsons. Hello. All right, so moving forward, we talk about chemical bonds. Now, atoms can combine with other atoms to form a chemical bond or a molecule. Molecules are the single pieces that make up a compound. So water, for example, is a molecule, and if we have a whole bunch of water molecules, it makes up the compound water. There are 2 types of bonds. There are covalent bonds and ionic bonds. Now, to get to the point of this, let me explain why things bond together. Atoms like to have full outer shells of electrons. We already said the electrons exist in the outer energy cloud. And for a lot of elements, they have an outside shell that can fit 8. And they want 8 electrons there. Well, some of them only have 6 out there, so they need 2 more. So they'll do one of 2 things. They will either share electrons with another atom, or they will take electrons away from another atom. And that's what ends up giving us chemical bonds. Those chemical bonds are made up of energy that hold them together. So let's take a look at the differences. A covalent bond is one in which atoms share their outermost electrons. For example, water. Oxygen has 2 electrons missing in order for it to be full. In other words, it's got 6 electrons on the outside and it wants 8. Hydrogen has 1 on the outside and it would like to get 1 more, right? So it could be 2. Well, if I take 2 hydrogens, they can share with oxygen, and that leaves me with H2O, or water. So water is a good example of a covalent bond. Now, that's a pretty strong bond because they're sharing. If they weren't sharing, then they could separate easily. Ionic bonds, on the other hand, are where an atom gives away an electron or takes on an electron. For example, sodium chloride. Sodium has 1 electron on the outside, and you know what? If it gets rid of that 1, it has a full shell right underneath. And chlorine has 7, so it only needs 1 more. So sodium will give away its electron, and chlorine will happily take it. Now, there is a point to mention here, and that is that covalent bonds are generally stronger than ionic bonds, and there's a reason for that. Imagine that this is your DNA, okay? Now, DNA is really important because the order of DNA tells us what we are as a person. Well, that means that we really want this bond between this part of the DNA and this part of the DNA to be very, very strong. Because if it weren't strong, then our DNA would fall apart, it would come out of order, and there's no telling what we would look like, right? So I don't want this bond to break. This is an example of a covalent bond. But I got to be able to get into my DNA to read it, right? So I need to be able to get in here. Well, if this bond were too strong, I would never be able to read my DNA, and then I wouldn't be able to use it. So this bond right here is actually a form of an ionic bond called a hydrogen bond. This is relatively easy to break. That way we can get in here, and guess what else? It's easy to form back together. So different ionic bonds, different covalent bonds, different strengths. And by the way, the stronger the bond, the more energy there is. And remember what I told you earlier, there's energy in those chemical bonds. We can get that energy out, and then we can use it. But we'll talk about that a little bit more in a minute. So in this example of DNA, we have covalent bonds and we have a special type of ionic bonds. These are very, very difficult to break. These are very easy to break. That's why it's important to understand why chemical bonds happen and what the difference is between them. All right? Now, when chemical reactions occur, bonds form and break, and that's called a chemical reaction. My old chemistry teacher used to tell me reactants react to produce products, and that's exactly what happens. Substances that go into the chemical reaction are called reactants. Substances that come out are called products, and so in this case we have water and carbon dioxide react to produce glucose and oxygen. Those are the products. So reactants are on the left side, products are on the right side, and we read this as water and carbon dioxide react to produce glucose and oxygen. Now there is something I want to mention. Hold that thought. I'm coming back in a second. I got to get something. Hold on. Because what we're talking about here is chemical reactions. Here I come. There's something that I need to mention. When things undergo, I'm back, chemical reactions, things change, okay? When substances undergo chemical reactions and bond with other things, things change. Let me give you an example. Chlorine is a poisonous gas. If you inhale chlorine, it will burn your lungs and you will drown in your own blood. I know, sounds like fun. Sodium, for example, is a element, that when exposed to water literally catches on fire. And I don't mean like smokes, I mean fire, okay? But if they bond together, sodium and chlorine, you end up with table salt, which we put on our food. Completely harmless. So that means a poisonous gas and a flammable solid react to produce a crystalline solid that makes food taste good. When things bond, the whole game changes. I'll give you another example. This is sucrose, better known as table sugar. Nice and sweet, yummy, delicious, a lot of energy in the bonds here, right? Well, keep in mind that sugar is made up of mostly carbon, hydrogen, and oxygen. So if I start to break this down, what I end up getting is carbon and water vapor. So if I take this, I expose it to a little hydrochloric acid, I get a whole bunch of energy and steam, and booyah, carbon, right? All I did was put some sugar in this little beaker, pour a little hydrochloric acid on it, and all of a sudden I've reduced the sugar back to its older form. So when you put sugar on your cereal in the morning, remember, this is inside of it, right? Now, keep in mind that when we broke those energy bonds, heat came out. So when I poured the hydrochloric acid here and I held this thing got really, really hot because the energy was being released from the sugar, and then the sugar was being reduced back to its other form, which was water vapor, H2O, and carbon. Alrighty, so let's move back to something else. Now that we know about chemical reactions, we can talk about a specific type of chemical reaction called redox reactions. When an organism gets energy from another organism, it's because of an exchange of electrons. Oxidation reactions are reactions where an organism is actually losing its electrons. Reduction reactions are reactions in which we're gaining electrons. So when these happen simultaneously, it's called a redox reaction. So what happens when we consume food, we take electrons, or in this case energy, from that and we add it to ourselves. So we oxidize that and we reduce it to ourselves. And what we're doing is basically converting energy from one form to another. And that's how we survive. That's how we get energy from the food that we eat. Now there is a point to remember here. This sounds confusing. Reduction is the gain. Wow, could they make that more difficult to remember? Because reduction, I think, is smaller. Here's how I always remembered oxidation reduction reactions. O-I-L-R-I-G. Oxidation is loss, reduction is gain. Oxidation is lost, reduction is gain, and in this case, we're talking about electrons. Why do we need to know about redox reactions? Very simple. That's how we get energy. That's it, right? All right, a couple other things we need to talk about here, and that is making reactions happen. Now, when chemical reactions happen, they do require a little bit of energy to happen, and that's called activation energy. There are some substances known as catalysts that can reduce the activation energy for a reaction, therefore making the reaction more efficient, meaning that the reaction doesn't require as much energy to happen. Catalysts are not used up in a chemical reaction because they're neither a reactant nor a product, which means that they can be used again. So reactants simply, catalysts simply make things happen faster and more efficiently. In our body, there are thousands of catalysts that we call enzymes that help with every chemical process. Why is this important? Well, the chemical... because the chemical reactions in our body could take really, really long time and could take a lot of energy. In some cases, they would take more energy than they actually produce. So we need catalysts to drop the amount of energy we're using to do these chemical reactions so that when we do them, we're getting a more efficient return. That way, our body's not spending all its energy on just doing chemical reactions, right? I mean, it would be possible to eat a candy bar with 1,000 calories, but we spend 600 calories simply on digesting it. Well, then we're only getting 400 calories. That's hardly worth it, is it? Now, if you're trying to lose weight, that makes sense, but otherwise it doesn't make biological sense because when we eat food, we're supposed to be getting energy from it. All right? So, let's move on just a little bit more here as we talk about states of matter. We've already hit on the kinetic theory of matter, and that the first part says that all matter in the universe is made up of atoms. What we have not talked about is the part where it says that atoms are in constant motion. The amount of kinetic energy or movement, and that's what kinetic means, is movement, and how close the particles all determine what state the substance is in. And when we talk about state, we're talking about solid, liquid, and gas. All right? Now, there is a difference here. Now, what I'm going to do is try to launch this animation here. We're going to open the hyperlink in a new window. Hang tight for a second. I'm going to show you a little animation that shows you exactly what this stuff looks like. If you see here, this is an animation from Purdue University. This diagram here shows a solid. Notice that it's moving just a little bit, right? A liquid, they're rolling over each other, all these little particles, molecules or atoms or whatever we're looking at. Here is a gas. Notice how fast they're moving and moving around. This has a higher kinetic energy than this, and this has a higher kinetic energy than that. Well, how do we measure kinetic energy? Simple. We measure temperature. That's right. Kinetic energy can be measured by temperature because the more the particles are moving, the higher the temperature of that particular substance is going to be. Pretty simple stuff. Now, that's about all we need. Let's go over our objectives real quick to make sure we've learned everything we need. First of all, we'll define the term matter. Matter is simply anything that has mass and takes up space. Everything in the universe is made up of matter, and matter is made up of elements. Elements are simply a whole bunch of atoms that are the same. For example, oxygen. All the oxygen atoms are the same. That means oxygen is an element. Compounds are made up of molecules in which all the molecules are the same. So water is made up of molecules that have 1 part oxygen and 2 parts hydrogen, and that's called a compound. So one molecule is the actual atoms that are stuck together. A whole bunch of those molecules equals the compound. Now, covalent bonds are where we share our outermost electrons. Ionic bonds are where we either lose or gain electrons. Covalent bonds are stronger and tend to have more energy than their ionic cousins. The parts of a chemical reaction include the reactants, which go in and are written on the left-hand side, and products, which are the things that come out and are written on the right-hand side. And finally, the kinetic energy of particles in the different states of matter are that gases are moving fast and collide, therefore they have higher kinetic energy. Fluids or liquids are closer together, but they are moving a lot, and solids actually only vibrate just a little, but they are in motion. I hope that this helps you understand the basics of chemistry. The next time I see you, we're going to be talking about organic and biochemistry, which is a subject that has made many of college students cry and wet themselves. So don't let that scare you, though, because we're going to make it simple and easy to understand. So come back to your e-biology teacher, and if you have any questions, ask me in class or watch this podcast again, and I hope that it helps. Later.